Hi, my name is Dai Matsuzaka, and today we're going to be working on Chapter 4.5, Graphing Exponential and Polynomial Functions. So, the exponential function is a function of the following form. So it's f of x is equal to c times a to the power of x plus b. So it kind of looks, like a linear equation. If you remember the ax plus b, like this. But instead of a just being a coefficient, now it's actually the base of an exponent, and x is the exponent here. And we add c as a constant, as a coefficient of the a to the power of x value. Let's look at the y-intercept. So the y-intercept is, if you recall, it's when x is equal to 0. But if you think about the rules of exponents, a to the power of 0 is just always 1 for any a. So then we just have that y is going to be equal to c times 1 plus b. So it's just equal to c plus b. Now notice that a is always non-zero. So a is not equal to 0. Because 0 to the power of 0 is just not well defined. The x-intercept is when the y value is equal to 0. And here's a couple things about the x-intercept, and it's just like the quadratic equations, where sometimes it just doesn't exist. In exponential functions, it might not exist as well. So it exists under two conditions. So if c is greater than 0, a is greater than 0, and b is less than 0, then the x-intercept exists. This is one case. So you can take, for example, y is equal to 2 times 3 to the power of x minus 7, for example. If we take y to be equal to 0, then yes, we can find some x value. Because if y is equal to 0, then we have 7 is equal to 2 times 3 to the power of x. We can find an x value such that this is a sufficient equation. Now, we could have another case where we have the c is less than 0, a is always considered to be greater than 0, and b is greater than 0. So notice that c and b have now swapped signs. Now if you think about this, it would be something like minus 2 times 3x plus 7. Now notice that this is actually the same thing, right? We're just moving a different side of the equation over to the other side when y is equal to 0. So these are the two cases in which the x-intercept actually exists. You can see that, like, for example, if you take y is equal to 2 to the power of x, y equals 0. There exists no such x such that it goes to 0. If you think about exponentiation rules, right? 2 to the power of some negative function, negative number, like 1, is just equal to 1 over 2 to the power of that, right? So 2 to the power of negative 10 would just be equal to 1 over 2 to the power of 10. Now, notice that this does get very close to 0 for a large number, like large x, right? Large value down here. So the more negative you get with x, the closer you get to 0, but you never actually attain 0. So the x-intercept just doesn't exist. If I were to graph this, it would look something like this. As you approach the negatives, right? This is the x-axis, this is the y-axis. You get closer and closer and closer to the 0 value. But you never actually cross the axis. So there is no x-intercept. Okay, so there's something called an end behavior, which we really want to be careful of when we think about graphing and we think about classifying these exponential functions, right? And the end behavior is just the kind of value approached by the function as the value of x expands to plus and minus infinity. So we're just basically asking, right? If we have a graph like this, for example, this is just y is equal to x, right? What happens if we go all the way as far as we can on the x-axis to the right and all the way as far as we can to the left? What's going to happen to our y value? And for y equals x, It's quite simple. If x goes to infinity, what happens to y? Well, y also goes to infinity, right? It's going up as much as it can. If x is going to negative infinity, what's y doing? Well, it's also going down, right? Negative infinity as well. But you'll see that there are some cases in which this is not so obvious, and some things to know as well about exponential and quadratic functions. So, for an exponential function, the end behavior as x goes to infinity is determined by the value c. It's this coefficient that determines it. So let's just think of the two cases. If c is positive, c is negative, right? If c is positive, then your exponential function is going to expound upwards. So what's your end behavior? Well, it's also going to go into infinity. What if c is negative? Well, the opposite's going to happen, right? It's going to open up downwards. So the end behavior, well, it's going to go to negative infinity. So this c, the sign of c, determines the end behavior for the exponential function. Now, as x approaches negative infinity, the end behavior approaches the value b. Since ax, the power of x, so this is a to the power of x, becomes infinitesimally small. So this is exactly what we were talking about previously. If you remember the exponent rules, right? A to the power of negative x is equal to 1 over ax. So if x is really, really large, right? So say x is like, oh man, like 1000, for example. Then you have 1 over a to the power of 1000, right? This is basically 1 over really large number. Well, what's 1 divided by a large number? Well, it kind of gets close to 0. It's not exactly 0. It's not 0, actually. But it gets very close to 0. It's very small. So when we think about what's going to happen on the end behavior of this function, you have to look at the b value, the constant that you're adding at the end of the equation here. So if I were to write this out, it's like y is equal to c times a to the power of x plus b, right? So what's the end behavior? Well, this term gets close to 0. So this whole term gets close to 0. So all that's left is this b value. So you might get something like this, where we're getting very, very close to some value, which is b. Right here. Okay? Now, polynomial functions are of the following form, where we have a1 times x to the power of b1, a2 times x to the power of b2, on and on and on. So we actually worked with this already, right? Y is equal to x. What is this? Well, this is just when y is equal to 1 times x to the power of 1. This is a polynomial. What about the quadratic formula, right? So y is equal to ax squared plus bx plus c. Well, as you can see, again, this is a polynomial, right? You have ax squared, right? And then you have bx to the power of 1, b times x to the power of 1. And then this, you might see, oh, there's no x. There is. It's just the power of 0. So you have c power of c times x to the power of 0. So you can see that the quadratic formula, or the equation, is also a polynomial function. So now you have a kind of a group definition for a lot of the functions that you've been dealing with. Now, the degree of a polynomial is the integer value, the maximum of all the b's being the exponents. If you think back to this one, right? What's the degree of this polynomial here? Well, what's the maximum degree? Well, you compare the 2, the 1, and the 0. What's the maximum value? 2. So what's the degree of this polynomial? The degree is 2. Simple as that, right? Even simpler example, what about y is equal to x plus 2, right? What's the highest degree? Well, this is actually 2x to the power of 0, right? So the highest degree is 1. That's it. That's your degree. The degree for y is equal to x plus 2 is 1. Now, the degree of the polynomial determines the symmetry of the end behaviors. If the degree is odd, the ends are non-symmetrical. If the degree is even, the ends are symmetrical. This might not make a lot of sense intuitively, but you've already worked with a lot of cases. Think back to degree 1 polynomial. Let's go with the most simple example. Y is equal to x. What is the end behavior? It's not symmetrical. One goes to infinity, right? And one goes to negative infinity. So these two are not the same end behaviors. But what about the other function that you're very used to as well? Y is equal to x squared. Well, it actually both expands to positive infinity on both end behaviors. So they're symmetric. Now, this theorem is just basically saying we don't need to know what the functions look like. As long as we know the degree of this function, say this is 1001, then you know that the end behavior is not going to be the same. One is going to go up, one is going to go down. It could be the other way as well. It could be up this way and down this way. So the coefficient of the highest power determines the direction of the end behavior. If a is greater than 0, then the graph approaches infinity as x goes to infinity. And if not, if it's negative, then the graph approaches negative infinity as x goes to infinity. What does that mean? What is a? Well, so we're just naming the coefficient on the leading, the degree, the power, the highest power to be a. So say this is x to the power of 1000, right? Plus b x to the power of 990 plus x plus c, right? This polynomial is very complicated. Who knows what this actually looks like? But what we can tell from just looking at this is, first of all, we have an even degree. So the end behavior has to be symmetric. Furthermore, if you assume that a is greater than 0, then we know that this end behavior has to go to positive infinity. So we have something happening in between, but at least we know that if we go far enough on negative and the positive side of x, we actually arrive at something that looks like this, where we're going upwards on both ends. If it was negative, if a was less than 0, then we have the very opposite, where we're now actually going downwards. As x gets larger and x gets smaller, the graph goes downwards like this. The end behaviors are symmetric, and they're symmetric downwards, given that a is less than 0. Now, the x-intercept or x-intercepts of a polynomial function graph are the roots or the solutions to the function. So knowing how to factor and solve polynomial equations allows us to find the x-intercept. The y-intercept is simple to find. Substitute x equals 0 into the polynomial equation. So say we have polynomial p of x is equal to x squared plus 2x plus 1. Now, you've seen this case many times. You can factor this right off the bat. X plus 1 squared, right? Well, the x-intercept is actually just the root of this, right? The solution of this function when this is equal to 0. What is that? Well, it's when x is equal to negative 1. So when y is equal to 0, right? Remember, the polynomial p of x is just y. So if y is equal to 0, then x plus 1 to the square is equal to 0. Then there you go. You have x is equal to negative 1. That satisfies this equation when y is equal to 0. So then you know that you have this x-intercept at negative 1, 0. So if I were to draw this graph, you have some negative 1, and the graph is going to cross here. Furthermore, we can actually go further, right? Because we know that this is the highest degree here is 2, so you want to look at this x here, right? And the coefficient here is just 1, it's positive. And because it's an even degree, you know it's symmetric, right? And if it only has one possible x-intercept, then that actually must be the minimum, right? Because if it were to go any lower, then there would be another x-intercept. But because there's only one, that means that the graph only touches the x-intercept at one point, like this. And the end behavior is up. So I actually already drew a pretty good description of what this graph should look like, this polynomial should look like on the graph xy graph. So now we have a interesting theorem about polynomial and remainders. And basically it just says that p of s, so say it's just any s, right? S is some number. Then what this theorem says is that p of s, the polynomial with evaluated at the point s, is actually equal to the remainder of the division, the polynomial divided by x minus s. Let's actually see if this works by examples. So say your polynomial is x squared plus 2x plus 1, as we have dealt with previously before, and s is equal to negative 1. So that means that x minus s is equal to x plus 1, and so the division x squared plus 2x plus 1 over x plus 1 actually just leaves us with x plus 1, because this can be actually factored, right? X plus 1 squared, as we saw on the other page here, x plus 1 squared. So x plus 1 squared divided by x plus 1 is just x plus 1. So what's the remainder? Well, the remainder is just 0, right? And so we need that 0 is equal to p of s. Well, is that true? Well, if you put negative 1 into these, right, you get 1, because negative 1 squared is 1, minus 2 plus 1 equal to 0. I'm not going to be doing a proof of this, but this is a good way to check whether or not your answers to the division is correct, and to quickly find the remainder given a polynomial division. Now, if this p of s is equal to 0, then s is actually a factor for p of x, meaning because p of s is the remainder for a division of p of x divided by x minus s, right? If the remainder of this is equal to 0, then what does that say about x minus s? X minus s is a factor for p of x. So that's what this is saying. So if you ever find an s such that p of s is equal to 0, like what we did over here, right? We can see that minus 1, right, evaluated is equal to 0, then x plus 1 or x minus minus 1 is a factor for the polynomial. So this is a cool way to kind of reinvent how to find factors, right? Before we were doing factorization and going from like the quadratic formula, but in this way we can actually just kind of use test points and see if this input works. We can try another example. X squared minus 1 equals 0. What is an input such that this polynomial is equal to 0? Well, let's actually let me clear up the board here. So x squared minus 1 equals the polynomial p of x. So what's a value of x such that this is equal to 0? Well, minus 1. Minus 1 works, right? P of negative 1 equals 1 minus 1 equals 0. What else? P of 1 works, right? 1 minus 1. 1 minus 1 is equal to 0. So what does that tell us? Well, it tells us that the factors of this polynomial include x minus 1 and x plus 1. And we can actually show that that is actually the factors for this polynomial. So this is a cool way to just arrive at factoring in just a different angle. Now, vertical asymptote is a vertical line defined by x is equal to a, where for some function, f of a is equal to plus minus infinity. What does that actually mean? So I think the best way to see it is just to look at it visually. Okay? This function, the y equals x function, does not have a vertical asymptote, right? For no point a does the function go to infinity. But let's think about this graph. It starts off here and goes off all the way up. And this is at, say, 1. And it comes all the way down. So what you're going to realize here is that at x is equal to 1, right, f of 1 is going to infinity. So 1, x is equal to 1. This vertical line is a vertical asymptote. It's a line in which the closer you get to it, you just get sent to infinity, a very high number. You can also have the other case where it goes lower. So it could be a case in which, say, a graph goes extremely negative, right? So for at the origin, f of 0, you have that the function is actually attaining negative infinity. You can actually have both. You could have the case in which, say, we're still approaching the origin. One side goes to infinity over here. The other side goes to negative infinity. So f at 0 is equal to plus minus infinity. And so there you go. This is a vertical asymptote. At any point in which the function, the graph, goes exponentially to infinity, right? And there's a line that it doesn't cross, then you know that that's your vertical asymptote. Now define a function as the following. So y is equal to 1 over x is a great example of a vertical asymptote graph, right? So as x approaches 0, what happens? Well, this gets bigger and bigger and bigger. So there's an asymptote happening at the origin. What about if you approach x from the negative side? Well, it's negative, so 1 over some negative number is negative. So if this negative number is getting smaller, 1 over a small negative number, like say 1 over minus 0.5, is negative 2, right? So you're actually, as this part, the bottom, gets smaller and smaller in terms of the absolute value, your fraction gets, in absolute value, bigger and bigger and bigger. In terms of the order, right? It's because it's negative. It's getting smaller and smaller. It's going to negative infinity. So what's the vertical asymptote? Well, it's exactly at the origin. X is equal 0. That's the vertical asymptote. That's just the y-axis. The y-axis is the vertical asymptote in this case. So here's a theorem that's really nice and useful. So given an irrational function, x is equal to a is a vertical asymptote if a is a factor of the denominator polynomial. So suppose that we have a rational function like p of x is divided by some other polynomial. Let's call this q of x, right? So if q of x can be factored into some form x minus a, x minus b, then for some p of x, then at these 2 points, so this is specifically a and b, you're going to have a vertical asymptote. Because if you think about it, as x approaches a, or as x approaches b, your polynomial is getting exponentially larger and larger and larger. So that's your vertical asymptote here. Now, notice that there is a nuance here. You have to be careful with what kind of polynomial is going at the top. For example, we have something like this. Continuing with the previous example, right? If they share a root, for example, at this point, right, we might think, oh, then this has a vertical asymptote at -1. X is equal to -1 must be a vertical asymptote. Well, you're close, but you're not actually correct, because this x plus 1 cancels out with the top. If you factor the top, you get x plus 1 squared divided by x plus 1. So what is this actually? Just x plus 1. So what this actually results in is a point that does not work. -1 is not defined because of the denominator being 0, but that is not a vertical asymptote because your graph actually looks like x plus 1. So what does this actually look like? Well, say we have x squared plus 2x plus 1 over x plus 1. This graph looks literally like exactly the x plus 1 graph, right? Y is equal to x plus 1. They seem identical, but at the origin, at the -1, right here, -1, this graph does not actually attain any point. To make that very clear, the graph looks like this. This is at -1. So -1 is actually not part of the graph, because if it was, then the denominator is 0, and that doesn't make sense. But for every other point, the denominator is not 0, so the division actually makes sense. And when you divide by the x plus 1, right, we had x squared plus 2x plus 1 divided by x plus 1. When we divide this, we just get x plus 1. So as long as x is not equal to -1, in which case we were dividing by 0, as long as it's not that case, we have x plus 1. So do we have a vertical asymptote? We don't. But we do have this non-existent point in the graph. So what is the lesson here? The lesson is you have to be careful with whether or not this factor at the bottom here is actually divisible. So this theorem works out as long as you know that the polynomial up here and the polynomial down here, once factored, don't actually share any factors. That's a key thing. Now, we can look at this following very complex rational function. But we can actually analyze like the vertical asymptote of this thing just by looking at the factoring on the bottom here of x squared plus 5x plus 6, right? That's just factorable as the x plus 2 times x plus 3, right? And you can check, but for now, just assume that at the top here, there are no shared factors. So x plus 2 is not a shared factor up here at the complex thing here, and x plus 3, the same thing, not shared up there. Then you know that you have to have vertical asymptotes at -2 and -3.